Okay, so further we are going to look into the various axioms and theorems of Boolean algebra. This is going to be a very quick introduction to Boolean algebra because Boolean algebra is covered as a topic in other courses, I guess, as well. So here we are just going to look into some of the laws that are going to be useful for digital logic design perspective, right? So as we will start with something which is very fundamental. We'll start with these three Boolean algebra equations that are the expressions for not, and or. So these are the Boolean algebra expressions. We are trying to give the this is the top part where the text is written. This is typically the Boolean algebra expression, and you are going to definitely learn this other representation which we call the circuit level or gate level representation of these three equations. So this is for the NOT gate, this is for the AND gate, and this is for the OR gate. So apart from the Boolean algebra expression, we are going to have a circuit level expression. This is more important while we try to draw circuits, right? So as you will see that any Boolean algebra expression is going to be ultimately converted to its circuit form that is ready for implementation, right? And on the right hand side, what we show is the truth table or the functional specification of that particular equation, right? So if you have a and b are the two literals or the two variables here, it can take, these are all binary or capable of taking only two states, 0 or 1. So you are going to have 2 to the power 2, which is 4 rows, right? So 0 0 0 1 1 0 1 1, and a dot b, which is the AND operation, is defined as if you have at least one of the inputs as 0, the output is going to be 0. The output is going to be 1 only when both a and b are 1. Okay. In case of OR, this is a OR operation. Here also you are going to have these 4 inputs because 4 rows, because the number of rows only depends on the number of inputs, right? If you have 3 inputs a, b and c, you are going to have 8 rows, 2 to the power 3. If you are going to have 5 inputs a, b, c, d, e, you are going to have 32 rows, 2 to the power 5. Okay, but the output will depend on what is the functional mapping, what is the uh, logical operation that is going on with these 3 inputs or 2 inputs or 4 inputs, whatever be the case, to create the output. So here we are looking at the OR function. The OR function requires you to have at least one of them. If it is 1, the output is going to be 1. Okay, so if you see both of them are zeros, only in this case this is 0. So here both of them are 1, so this is 1, otherwise 0. Here both of them is 0, it is 0. If at least one of them is 1, it is going to be 1. So 0 1 it is 1, 1 0 it is 1, 1 1 also it is 1. At least one. Even if both of them are 1, that still the statement still holds, right? At least one of them is 1. Okay, and this is the complement also. It is not, or often it is called a complement operator. Okay, so not of a, it is often written as this bar, right? So you will come across different notations. One is sometimes called a not or a bar, or sometimes you can also come across a prime, right? So this mark, this both of them often mean not, right? So depending on which book you are studying and all, there could be minor differences, but typically they will mention in the beginning of the chapter what not, what is their nomenclature, what is the nomenclature they are using for indicating not. Okay, So dot is typically and plus is typically or. Okay, so these are the three simple Boolean algebra operators to start with. Okay, and here it's an algebra of this ones and zeros with these operations and or not. So you are going to frequently look at this fundamental Boolean algebra operator and or and not, and all of these are going to act upon inputs that are binary. So the inputs are always going to be either 1 or a 0, and you can of course have multiple inputs. That is another thing, right? So your truth table can have as many inputs, right? And I'll also discuss later, outputs can also be multiple, but every output has to be modeled separately. So individual outputs is going to be a function of the all the inputs. Okay, so this is going to be an algebra of ones and zeros with the fundamental operations and or not. You are going to start with a basic set of axioms. So that is something that we assume to be true before we delve into this topic. So those are known as axioms, and then you will derive some laws and theorems that is going to allow you to manipulate these Boolean expressions, right? So your expressions might not be as simple as just A and B or B and C and so on, but you are going to have, you can possibly have an enormous expression which is going to have a lot of various inputs, and they have different kind of operations going on in between them, and you might need to simplify that particular expression to make sense out of it, or maybe translate that particular expression into a circuit. So you might require that the expression be simplified, because a complicated expression might lead to a complicated circuit, and a complicated circuit could require more number of components, more number of gates, the energy consumed by the circuit could be more. There are many such reasons, right? So typically these laws and theorems are going to allow you to manipulate any Boolean expression that is typically meant for simplification of this Boolean expression. Okay, and why the simplification is required, I just now mentioned. I'm reiterating that all these Boolean expressions for our context is eventually going to be translated to some kind of a digital circuit, right? Somebody is going to take your design, or you yourself is going to take your expression and translate that into a circuit level design. And if you have if you have an expression which is fairly complicated, your corresponding translation to the circuit level design is also going to be complicated. Okay, and this is not good for any of us, because complicated design leads to an expensive it's an expensive proposition, and also it is not efficient. Okay, so often we will come across situations where we need to really simplify Boolean expressions as much as possible, and better is your handle on these laws and theorems, you will be in an advantageous position to make these simplifications effectively and meaningfully. Okay, and more sophisticated property is useful for manipulating digital designs representing in the form of Boolean equations. So you can derive other things. Okay, so maybe I give you a circuit which implements a particular Boolean expression. Okay, so maybe we will come across a Boolean operation called XOR, right? So this Boolean operation is implemented in terms of and or not, right? So this could be using some, let's say if you want to do A XOR B, this could mean you can either do A B or A bar B bar, let's say, right? Or there is another operation called XNOR. You might this is XNOR, and then you can actually have A bar B plus A B bar, right? So if you see XOR and XNOR, these are actually implemented in terms of, again, and or and not, but these expressions might be something that you have to use, right? So the design might ask you that you have to use these XNOR operations. or XOR operation. So it's just the high level simplification is not sufficient. You might have to derive some other expression which basically is going to constitute of this expression. So you need to kind of juggle these expressions as well as these laws and theorems, and you need to know the axioms well in order to create these designs. Okay, so these are the set of axioms. Any book is going to have that, but I am just going to do that for the sake of completeness. That is an important prerequisite for digital logic design. The first one is the set on which we are going to operate on. So B is basically your Boolean set, and it contains this at least two elements 0 and 1 such that they are not the same. 0 is not equal to 1, and we don't typically think anything beyond that, right? So 0 and 1 are the two states that are going to exist for any digital or binary bit that we are going to work with. Okay, so that is just a formality, and then we define all these properties on top of that set B for various operations, right? So if A and B belongs to this set B, so small a small b belongs to this capital B set, we define the closure property, which basically says that if you do any operation with A and B, that is going to give you a result which is going to end up in the same set capital B, right? So this is defined as the closure property. So result of result of and or stays in the set you start with. So we started with a set B, right? We started with a set B. A and B, small a and small b belongs to B. So if you do any operation, right? Let's say you do some operation F on A comma B, you get an output. Let's say output out. So this out has to belong to B. Okay. So this is what we mean here by the closure property, and or and operation support that. Okay. Then we have the commutative laws. A or B is equivalent to B or A and B is equivalent to B, A and B equivalent to B and A. So for primitive and or of two inputs, the order doesn't matter. Okay. So A is here value which is going to A can take value 0 1, B is the same, and the order doesn't matter. Okay. So the next thing are the identities. So if you or A with 0, okay, this is equal to A again. Okay, 0 is basically the false or and here or low or whatever, right? And 1 is like 1 or true or high. Okay, and A and with 1 is going to be A itself. Okay. Then there are distributive laws, which is fairly important. I think this is one of the most frequently used things that you are going to encounter, apart from De Morgan's laws that we are going to see next. So this is A plus B dot C is equal to A plus B dot A plus C. Okay, so you can fairly almost see as like a factorization that has happened, but this is for Boolean algebra. So A and B here are logical variables. So A or B, and the whole thing is going to be ANDed with A or C. This is equivalent to doing A or B and C. So B and C, if you combine and find out this value, and that value is ORed with A, is the equivalent thing is A or B and A or C. Similarly, if you look at the other expression, the second expression, A dot B plus C is equal to A dot B plus A dot C. Okay, so that is why it distributes over plus, just like regular algebra that you have done in your high school. Okay, so please keep these things in your mind. So the distributes over plus, but plus distributes over dot, right? So you have to just remember these two expressions. Okay, and this is really useful later when you want to simplify expressions or try to manipulate expressions. This will be really handy if you remember this, recall this. Okay, so here this is A or A complement. I think this is not very clear here. A or A complement is going to be 1 and A dot A complement is going to be 0. Okay, so you are ANDing A, which is logical, which is a logical variable, and you are ANDing that with A bar, right? So both of them cannot be simultaneously true, right? So if A is true, A bar has to be false, right? And if you take an AND of both of them, your resultant value will be low or 0 or false or whatever be the convention you are having. And A plus A bar, right? So whatever be the value of A, if it is 0, if it is 1, doesn't matter, and you OR that with A bar, that is equal to 1 all the time, because A could be 0, in that case A bar is going to be 1, so it is going to be 1. If A is 1, then you OR it with A bar, which is 0, so 1 plus 0 is going to be 1. Okay, so I would encourage you to plug in actual values of A, B and C and try it out yourself and just be satisfied that these expressions make sense. So you can even draw a truth table and try these things out. And one more observation that we should have here is the axiom duality. So all the axioms come in dual form. So anything true for an expression is also true for its dual. So what we are trying to say is all the expressions that we have seen here or any other Boolean algebra expression that we are going to see later has a dual form. Okay, so a dual expression is basically flipping some of the operators and changing some of the zeros to ones, right? So any derivation you can make that is true can be flipped into its dual form and stays true. Okay, so suppose you have some expression, I am defining this by a function on this Boolean variable, let's say A, B and C. So it leads to some kind of an output, and you can actually have a dual form of D, which is going to be acting on the same output, and this basically remains true. Okay, and here we are trying to say that, okay, how can you create the dual form? Maybe you want the dual form because creating a circuit in the dual form is easier for you. Okay, there might not be any specific reason, but you just want to know that every Boolean expression has a dual form, and this is the axiom for duality. So every AND operation is going to be replaced by an OR operation. So suppose you had A and B in the expression, that is going to be replaced by OR. Every OR operation is going to be replaced by an AND operation. Every constant 1, I think here there is something missing. So every constant 1 with 0 and every constant 0 with 1. Okay, but do not change any of the literals or play with a complement. So we are not really going to touch A bar or B bar and change them, right? So we are simply changing the AND to OR to AND, ones to zeros, zeros to ones, but we are not touching anything that has complements. Okay, so A bar remains A bar, B bar remains B bar. Okay, so this is just a note about the duality. So for example, if you have A dot B plus C, this could be written as, you can change it to plus dot is going to be replaced with plus. So this is going to be replaced with plus, and B plus C, so plus is going to be replaced by a dot. Okay, so this is what the expression is, and here you can very easily show that this is satisfying the distributive law, right? So you can easily derive that by the distributive law. So they are equivalent. That is what we are trying to say, that even if you have the dual form, the expressions that you are going to get are equivalent. Okay, so it can be simplified to A plus B dot A plus C, and here you can simplify it to A dot B plus A dot C. Again, if you do a dual here, you can see the dots are replaced by plus dots are replaced by plus, plus is replaced by a dot. Okay, so this is one example of how do you take one expression and find out its dual, and just be convinced that the duals are equivalent expressions. Okay.